All right, here's the solution to Wednesday's Do Now. A lot of people are missing class today. So here it is. This is an important problem to go through because this is something you could be asked to do on an AP exam, on the AP2 exam, and it has some good review concepts from magnetism and electrostatics. All right, here we go. The allowed energy levels of a hypothetical atom have principal quantum numbers n equals 1, 2, 3, and 4, energies of -8 electron volts, -5 electron volts, -2 electron volts, and -1 electron volts. Draw the energy level diagram for the atom. Label each level with the appropriate energy and principal quantum number. What you should remember from chemistry, n equals 1, that's the ground state. So I'm putting that down here. This is the ground state. That's n equals 1. Then let's see, n equals 2 would be have a level of -5. So let's see, 1, 2, 3, use this. N equals 2, this would be -5 electron volts. The next one, n equals 3, is going to be here. 1, 2, 3. N equals 3, -2 electron volts. So I'm using the lines on the screen here as a scale. And then the next one will be n equals 4, -1 electron volts. So here are the energy levels. When you get to 0 or infinity, that would be n equals infinity, and that would be an ionization. So not that you're asked to, you would need to do this, but you could put in n equals anything greater than that. N equals beyond 4, you get ionization. Not that that's necessary. So let's draw the diagram. Part 1 is done. Moving on to part 2. Calculate the energy of calculate the frequency of a photon that will excite it from the ground state to n equals 3. That would be taking an electron from here let's use orange. Taking an electron from the ground state up to here. So it's got to absorb a photon of 6 electron volts, going from -8 to -2. It's got to absorb an electron of 6 electron volts. From n equals 1 to n3, you need to add 6 electron volts. There are 2 ways you could go about this problem. Okay. You're going to use the equation E equals HF. Now you have the energy, but you can get the energy in electron volts. The key thing here is H on the front page of your reference tables or equation sheet. H, Planck's constant, is presented to you in 2 ways. 6.626 times 10 to the minus 34th joules seconds, or, this is quite nice, this is going to be helpful here, or 4.14 times 10 to the -15th electron volts multiplied by seconds. This right now, since we were given the energy, or since we just calculated the energy in electron volts, we can keep with this one. So energy, we got 6 electron volts equals 4.14 times 10 to the minus 15th electron volt seconds times frequency. You do that math, pretty straightforward. You should get the frequency to be 1.45 times 10 to the 15th hertz. Right? Electron volts will cancel electron volts, and you get per second, which is what frequency is, cycles per second. So there you go. That's not hard, but important to recognize. Planck's constant can be in joule seconds or electron volt seconds. Now, third part of the problem. A photon of a wavelength 124 is incident upon the atom and causes the electron to be ejected. So that tells me that a wavelength of 124 will take the electron from here and go beyond ionization. It will ionize it. Neglecting relativistic effects, calculate the speed of this electron. Here we go. So first thing you want to do is you want to convert that into energy. How much energy is that? Okay, that's the first step. Energy equals HF. Now we have nanometers. Now we got meters, so we got to go energy in joules. Energy equals 6.626 times 10 to the minus 34th joule seconds times, I should say we got this. So remember, this is HC over lambda. So 3 times 10 to the 8th meters per second over 124 times 10 to the minus 9th nanometers. Okay? If you do all this math, this is important. I kind of went through that fast, but there are two equations for, you can take E equals HF, but since F equals C over lambda, E equals HC over lambda. Okay, now when you do that arithmetic, you will get that the energy of the photon is 1.6 times 10 to the negative 18th joules. Pretty easy. This is energy in joules, but our energy level diagram is in electron volts. So let's see, how many electron volts is that? 1 electron volt equals 1.6 times 10 to the minus 19th joules. So this is a factor of 10. This is 10 electron volts. The energy is 10 electron volts. So back to our energy level diagram. If a photon of 10 electron volts is incident here, 10 electron volts is going to take this electron. 8 of those electron volts will be used here, and this is going to come off with 2 electron volts. It takes 8 electron volts to ionize. It'll have 2 left over. 8 electron volts to ionize, 2 electron volts, I'll call it extra. That will be the energy of the electron that gets kicked off. Well, kinetic energy equals 1/2 mv squared. So we have 2 electron volts. That's the energy that'll be turned into 2 electron volts. But wait, if I do this in mass and kilograms, I can't have this in electron volts. 2 electron volts. Very important to remember our, wrong way, our 2 electron volts is really using this conversion, 2 electron volts is really 3.2 times 10 to the minus 19th joules equals 1/2. It's an electron, which has a mass of 9.11 times 10 to the minus 31 kilograms, v squared. There's your equation. And when you do this arithmetic, you will find out that the velocity of the electron, right, multiply both sides by 2, divide by 9.11 times 10 to the minus third, take the square root of all of that, you will get the answer to be 8.38 times 10 to the 5th meters per second. Because using 2 electron volts, which is this many joules, putting out the kinetic energy equation from there. Now, the fourth part of the problem. The ejected electron enters a region of space that contains a constant uniform magnetic field. The electron is moving to the left. Very important to recognize it's an electron, which means it is negative charged. So here, when we're doing magnetism, it enters a magnetic field. With negative charges, use your left hand rules. The B field is into the page. So take your left hand, fingers into the page. Thumb, velocity, left. Fingers into the page, left. The palm is the force that the thing feels, and your palm should be facing up. So as the electron goes here, the magnetic force is going to push it up. On the diagram below, draw a possible path. So as the electron enters here, it is going to be pushed up. Something like that in a curved circular path. That's a possible. Who knows how the strength is? It going to be a really tight spiral? It's going to be a gentle spiral? We don't know, but it's curving up. Describe what happens to the speed as it passes through. The speed doesn't change. It doesn't gain speed or lose speed, but it does change direction. The magnetic force is perpendicular to the velocity vector. So the force doesn't make it go faster, doesn't make it go slower. The force only changes its direction. So describe what happens to the speed. The speed doesn't change. Explain why this happens, because the force is perpendicular to the velocity. To make this electron go in a straight line, you could apply an electric field in that region. Which way would the electric field have to be? All right. Again, we have this space where there is somewhere on a negative charge, there is a magnetic force this way. Okay? Can't erase that for some reason. On this negative bit, there's a magnetic force there. We need an electrostatic force. To make it go straight, we need an electric force that way. How are we going to get an electric force on a negative bit down? We have to put a negative plate up here, because negatives repel negatives, and a positive plate down here, a positive. All right, we're going to make a capacitor, a parallel plate capacitor. And this parallel plate capacitor would push an electron down. Which way is the electric field going to be? Electric fields are always drawn from positive to negative. So the electric field is this way. The E field always goes out from positive and into negative. And if we put a negative bit there, that would push it down. So to make an electron travel in a straight line, what direction is the required electric field? The E field must be toward the top of the page or up. Why? So that if you put the negative plate of the parallel capacitor up top, the electron will be repelled by the parallel plate, forced down. Okay, that's really all there is to it. Problem solved.